thank you very much. We had a discussion session just before this lecture, and there I explained that I like to chop big questions into pieces, try to get as many as possible small questions, and try to answer these first, and then see if you can get the big picture, and then arrive at answering bigger questions. That always has been my philosophy, and I still think that here also we have to do this. So I also explained in that discussion, by the way, what I think of quantum mechanics and the role it plays in modern physics. I think quantum mechanics is a tool, a machine invented by humanity to understand what we see happening around us. However, that doesn't mean that nature itself is described by a Hilbert space. The Hilbert space could be a technical tool, and I still like to regard it as that. And there I also briefly explained an example where exactly this happens in physics. The example is called the Ising model. One of the more elegant ways to solve a complicated mathematical question called the Ising model is to turn it first into a quantum field theory, then answer the question, and then just isolate the classical part of the answer, and then you get the classical answer to a classical question. So could it not be that quantum mechanics as you know it today is something very simple, very similar? That it could be that quantum mechanics is not in the ultimate laws of physics at all. Quantum mechanics is in our set of tools to solve very complicated equations. In that set of tools, you also have complex numbers, which might have nothing to do with the real world after all, but they are just part of our mathematical analysis. Just like when you solve a complicated integral equation, and the integral equation has nothing to do with complex numbers, but complex numbers are useful in solving it. Even real numbers, I believe, are man-made constructions to make life look simple and to make it accessible to an analysis that we can handle mathematically. Doesn't mean that the real numbers are fundamental notions in the fundamental theories of nature. I now even have grave doubts there. Nature is basically simple, and the one thing that possibly may survive in the ultimate laws of nature is just the notion of information. How is information being processed? And I think that's a very fundamental question. We see that happening with quantum black holes. When you look at tiny enough systems in nature, then black holes are the most generic constructions you can think of. And then you count the number of states in the black hole, it's only finite. So we are at the very tiniest scales in nature, we only have to deal with finite integer numbers, not with infinite numbers, not with real numbers, let alone complex numbers, and so on. All that is fine, but how does it work? And I'm going to need a lot of time to explain things I'm going to talk about, so I'm not going to waste my time in first listing the table of contents. I hope this set of slides will become available on the net, just like that of the previous talk. And when you want to look things over, you can always look at the various subjects. So this is roughly what I'll try to talk about. I don't know whether I'll reach the end or not. Let me first explain a simple example of the kind of models and the kind of mathematics that I like to talk about. And one is based on one of the simplest quantum mechanical systems, the harmonic oscillator. The harmonic oscillator is a particle, but it could be a field, it could be something else, anything that vibrates. In fact, I now believe the harmonic oscillator describes anything that is periodic. That's really the only thing you need to know about it. But anything that vibrates, of course, is periodic. It has a period T, and it can be characterized as an object living in a parabolic potential well, and it has energy levels which you can easily compute by solving the Schrödinger equation in a parabolic potential well. And you find the energy levels are described by an integer plus 1/2 times a unit, and that unit of energy is directly the unit of energy relevant to a harmonic oscillator. It's h times nu, where nu is the frequency of the oscillator, and h is Planck's constant. Now what you can do with this model is you can turn it into something classical. And this often surprises people when I say that. The quantum harmonic oscillator is thought to be a fundamental quantum thing. However, suppose that you say, well, yes, but I can't reach the infinite energy states. They're too far away. Let's concentrate on the first n finite energy levels. Then perform a discrete or finite Fourier transform of these n states. Then you find something quite interesting, remarkable, pleasing, if you will, that those n states can be imagined to lie on a circle, and the evolution law of this oscillator then tells you that after a fraction of the period, you go from one state to the next discrete Fourier transform, to the next, and it goes into circles. The period of the entire circle is the same as the period of the harmonic oscillator. But now you see the circle is divided into tiny bits, and the number of bits the circle is divided in is equal to the number of energy levels you took along in your finite Fourier transform. Now you can imagine, let's go all the way to n to infinity, then this discrete hopping circle goes into the continuum, and then you have a particle rotating on a circle with, again, a periodicity of the same period of the harmonic oscillator. So in a sense, the harmonic oscillator seems to be mathematically related to particles moving on a circle. The particle moves along the circle at a constant speed, so 1 radian per second, if you will, and as such, that object seems to be totally classical. But even after the finite object is in a sense classical. After certain distinct classical steps in time, it just hops from one state to the next. There's no dispersion, there's no quantum superposition at that level, it's just classical. And in this sense then, the quantum harmonic oscillator seems to be equivalent to a classical system. You have to know the transformation rules, that's always the case. So if n is finite, your time is a discrete mesh of time values. On that discrete mesh of time values, your system is completely deterministic. If you choose other time values in between, then you get back your whole quantum picture. So in the quantum harmonic oscillator, you have the familiar operators x of t and p of t, x being the deviation and p being the momentum of the oscillator, and they exchange roles all the time. But now this angle phi, or the label of these discrete states, are objects that seem to evolve classically. I call these things Beables, in honor of John Bell, who thought a lot about these topics, and he realized that operators are sometimes observable and sometimes their value is subject to uncertainty relations. But these objects are not subject to uncertainty relations at all. If they are sharply defined at one time, they continue to be sharply defined at later times. No dispersion, no uncertainty. So these are objects actually, I call them script B for Beable. There could be more than one of them, and they have the property that they commute. As operators, they commute at all times. So quantum mechanics becomes trivial. You might say ugly, you might say non-quantum mechanical, you say all these things, but basically the harmonic oscillator turns into something utterly trivial by this argument. It's nothing else than something moving periodically on the circle. It could be periodically in some other concepts. Anything being periodic in nature, you can play this trick and say, actually, I can find a set of Beables. Using these Beables, you can set up a basis of Hilbert space. I would call that the ontological basis. If I rephrase the laws of nature of the harmonic oscillator in terms of its ontological basis, you will see only deterministic evolution. You won't see quantum mechanics at all. And of course, you will be asking, what about quantum superposition, all that? I'll come to that. So quantum superposition may well be a man-made complication that doesn't have anything to do with the real thing that's happening physically. Now, I like now to mention a simpler, a more complicated actually, and more interesting model where the same thing can be done. It's called massless chiral neutrinos. They are very trivial neutrinos because they are non-interacting. So again, you could criticize me here by saying your model is not physically interesting. These neutrinos are non-interacting. Yes, but they are neutrinos, and as such, they are normally regarded as ultimately quantum objects. A neutrino is a quantum particle. It's the energy quantum of the neutrino field. And neutrinos are emitted one at a time when you have a radioactive decay or something like that. In all respects, neutrinos look like electrons and other fundamentally quantum particles. Yet, in the limit that you take them massless, we now know neutrinos do have a mass, so it's not exactly true what I'm saying here. But take the massless limit, where you can also take them to be chiral. That's to say they only rotate in one direction. Their helicity can only have one value. Then the fundamental Dirac equation of the neutrino is a 2-component equation rather than 4 components, because the spin can only be in one rather than 2 directions. And you have neutrinos and antineutrinos, so still 2 states, but not 4 like in the case of the electron. I want to distinguish the second quantized theory from the first quantized theory. The second quantized theory has a familiar fermionic field psi, and the Hamiltonian would be psi dagger times sigma dot p psi, where p is minus I times ddx. So the top line has, or the second line has the Hamiltonian for the second quantized theory. But let me first look at the first quantized theory, describing a single neutrino and the whole of its antiparticle. So like the Hamiltonian is then sigma dot p. That's the Hamiltonian which you later put in the second quantized theory. I mentioned the second quantized theory because I'm going to return to it. But let's for a moment consider the Hamiltonian described by that very, very simple Dirac equation. I cut the Dirac equation into smaller pieces to make my question simple. And that's the simplest Dirac equation I can write down. In that equation, I'll claim I can define a set of Beables just like for the harmonic oscillator. I call them now script O, for reasons I've forgotten now, by the way, but I could call them B as well. But these Beables, are now a bit more complicated in a harmonic oscillator, but equally or even more interesting, because here you might not have expected it. And the Beables are P hat. P hat is the orientation of the momentum vector, but not its length. Its length has been divided out. It's actually plus or minus the norm of the vector P. I will define the sign in a way different from usually. Usually say P hat is always positive. It is P divided by its positive length. But P hat is now a unit vector in the direction of the momentum or in the opposite direction. I'll specify that later. Actually, I can specify it right now. I can say the total vector P itself is P hat times P absolute, or minus. I'll let the minus sign depend on the sign of the Z component, for instance, of P, such that P hat always has a positive Z component. It's just a technicality, but technicalities are sometimes important. Then the operator S, which is the spin in the direction of P. Well, actually, that is always positive, but it could be negative if P hat itself is oriented in the opposite direction. So S in the spin in the direction of motion can be positive. In the opposite direction of motion, it will be negative. So S is plus or minus 1. And then R is the position of the neutrino, but only that component which is parallel to its momentum. Now, our claim is that these are altogether form a set of Beables. It is not so difficult to prove. I won't prove this now in detail, but this is something you can do nearly on the back of an envelope. It's not particularly hard. The momentum P obviously Maybe there's something with the battery. I'll use this. So, can you hear me now? Yes, it should be. Okay, so the components of the momentum tensor obviously commute with each other. So the two independent components of P hat commute with each other. The fact that S commutes with P is also trivial. The sigmas commute with the P, so the S commutes with P itself. It only has one component. The only thing that's not quite trivial here is whether the coordinate R commutes with P hat. Actually, that's not so difficult to prove. R, apart from a factor P absolute, R is a dilaton operator. But P hat has length 1, so it does not change under a dilatation. Therefore, P hat must commute with R. You have to think a little bit whether this argument is correct, but I claim it is correct. And actually, you can explicitly compute and find that R commutes with P hat as well. Not only that, they commute at all times. That's because the equation of motion is very simple. The ddt of P hat is 0, the ddt of S, I forgot to mention S there. The ddt of S is 0, and ddt of R is actually equal to S. So because of this, all these things, when they commute at one time, they commute at all times. So, and actually you can now prove that if you know all eigenstates of these three operators separately, then you have a representation of the entire Hilbert space of a single neutrino. So they form a complete set. What does a complete set actually describe physically? Well, I claim it describes a sheet. I call that a neutrino sheet. And that's because the position in the direction of P hat basically defines where the sheet is lying, because it does not define the transverse coordinates, but only the longitudinal coordinate. So that's typically the way to describe a membrane or a sheet, flat sheet, going in one direction. S is the velocity of the membrane, but either the membrane can go to the right or can go to the left with the speed of light. So S just tells me in which direction the speed is moving. Does it move this way or the opposite way? And then R tells you what the position of the sheet actually is in that particular direction. So R obviously increases in time or decreases in time depending on the sign of S. That's all. And the orientation sheet remains constant. So yes, the neutrino is just physically equivalent to a classical sheet moving with the speed of light in one direction. And now you can think of, let me first tell you something else. I did a calculation, and I thought it would be an easy calculation. I spent several days to figure out the right expression, because it turned out not to be easy at all. I took the Hilbert space of these three coordinates which I had here. So the Hilbert space of R, P hat, and S. And I took that Hilbert space and asked, now, how do I express the original operators X and sigma and the original P in terms of these operators? That should be simple and straightforward. It wasn't so simple and straightforward. This rather complicated looking expression was the way to express X. What goes into there is the inverse of the PR operator. That's basically an integral operator. You have to define it. And in particular, when PR is 0, there is a problem defining X, of course. That's a neutrino sitting at infinity somewhere. And I have a lot to say about such zeros, but I will refrain from that now. There's also an operator L, which is the operator that generates a rotation of the sheet. Okay. L is the operator that just rotates the sheet, and that operator comes in to the expression in a remarkably complex way. And then not only the operator S, which I call here S3, but also two spin flip operators, S1 and S2, which together with S3 form a set just like the Pauli matrices. So you have an Sx, Y, Z, but now it's S1, S2, and S3, because they are oriented with the sheet. And there are some operators theta and phi which are just components, they're functions of the p hat operator. And I haven't written down what they are in detail because there's so much complexity in this. This took me a long time to get this completely without errors because now you have to prove that the different components of X commute, and you have to compute the p operator, something similar, and then compute that p and X have the delta commutator, and that you can also have similar expressions for the Pauli sigma matrices, and again they obey the Pauli sigma commutation rules. So all is fine with this expression, but you have to do some work with it. The only thing you have to watch out for is the zeros of the PR operator, which is DDR basically. So when a function is independent of R, DDR is 0, then there's a difficulty with defining X. Well, of course, if you're a plane wave, you can't really define the X operator. So that should have been expected. Anyway, the Hamiltonian of this first quantized neutrino has no ground state. And you could see right in the beginning that H is sigma dot P is linear in the momentum P, and P can be positive and negative. So this certainly doesn't have a ground state. The question now is how to do quantum mechanics with things that don't have a ground state. Well, fortunately, this difficult question has been answered by Dirac in an absolutely magnificent way. And the answer was second quantization. If you second quantize, you just take the positive energy states, you take the negative energy states, and you declare the negative energy states to be annihilation states for antiparticles rather than particles. So neutrinos have to be divided into antiparticles and particles. A hole in the antiparticle is the negative energy particle. And all is well according to Dirac, and he was right. So second quantizing the system gives you back your ground state of the Hamiltonian, and now you can do real physics with this. So, of course, the price you pay is you have to have an indefinite number of these sheets. So the whole universe is filled with these neutrino sheets. For every neutrino, there's a different sheet. And then you can work out all the rest by second quantization. It's a lot of work. It can be done. And this is an example where you see that a classical thing, a classical fermionic field, obeying a fermionic Dirac equation actually, or a quantum fermionic field, actually turns out to be equivalent to classical sheets moving with arbitrary numbers in the background. Now, you could regard these classical models, both the classical harmonic oscillator going around in circles and the neutrino sheets going like that, as an automaton. It's a system that you can put in your laptop. You can say, if I know where the sheet is now, I can calculate where the sheet will be a second from now, and so on. Same thing for the harmonic oscillator. So a thing you can program in your classical laptop. Don't use your quantum laptop. It doesn't exist yet. You use your classical laptop. That I'll call an automaton. And the simplest example of an automaton is a system with just n states, like what I did with the harmonic oscillator. And the automaton will then be described by an evolution operator, which will be a permutator for these n states. It doesn't have to be the displacement operator. It could be any complicated permutation operator. And now I do something which sounds innocent, but it's actually very complicated. In mathematics, it's well known. If you want to study the permutation group, you have to find the representation of the permutation group in terms of vector space. So I introduce Hilbert space just in order to describe the representations of the permutation group. It's a mathematical trick, but be aware that this mathematical trick replaces my automaton with a quantum theory where I have a Hilbert space. It's a finite dimensional vector space now, but it's easy to extend that to think of a system that can evolve to infinitely many different states. And so you have a permutator which lives on the space of infinitely many objects, and then Hilbert space becomes infinite dimensional, and the permutator is suddenly an operator in Hilbert space. Now it's again a rather elementary physical exercise to say that this operator, I would now call it U, tells you what happens in a time step delta t, which might be very small, to rewrite that as the exponent of an operator A. And A will be the Hamiltonian times delta t. So that defines the Hamiltonian of a system. Now, since U is a unitary operator, the permutations in this representation are unitary operators. So this operator is unitary, and therefore its eigenvalues lie on the unit circle. That was in Daniel Schoenheimer's talk, this unit circle, all the roots of 1. And so the permutator then that tells you that you can put the states on the circle, and now you can ask how they evolve. Now, to rediscover h out of this is easy. You just take the logarithm. Unfortunately, there are very, very many solutions because logarithm is multi-valued. One solution is given by this expression is not completely right because it's wrong for one state only. Because what you do when you take the logarithm of the unit circle, you open up the circle, make a line. But the question is what to do with the endpoints. The endpoints of that circle are the one points where this procedure runs into subtle mathematical technicalities that I won't go into too much. But on these endpoints, the system fails. Now, the endpoints happens to be the point where the Hamiltonian is extreme, either the lowest value or the highest eigenvalue. So the highest eigenvalue of this Hamiltonian coincides with the lowest eigenvalue in terms of the Hilbert space, but not if you open up the Hilbert space. That means that for the lowest eigenvalue, which is the vacuum state, this expression is wrong. But for all states it's right. For all states it's correct except for the vacuum state. And so this is a summation, and the summation converges reasonably well, but it is wrong for the vacuum. For the vacuum, U is 1, and then you get pi instead of 0. The Hamiltonian should be 0, but here it comes at pi. So I have to correct this, I have to add minus pi times the delta function when the energy of the state is 0. But that's, again, a technicality. The analysis of the work I did after this contains lots of such technicalities, in particular of states which are lying on the edge of a domain. I call those edge states, and these edge states have to take into account. What is a cellular automaton? A cellular automaton is just like an automaton, but its states are defined on a lattice. A little bit like the Ising model, but now I can take a three-dimensional lattice, I can take an n-dimensional lattice, but put it on a lattice. Then it looks a little bit more like our universe. In the limit that the lattice becomes continuous, it looks like the standard model in a way. Except that the standard model is not classical, but quantum mechanical, of course. Now, actually, there's a very nice way to describe the evolution on a cellular automaton by saying that okay, time runs horizontally here, time runs vertically here, space runs horizontally here, but space could have 3 instead of 1 dimensions. I've only drawn a one space, one time automaton here. And typically in an automaton you assume the interactions only to be between nearest neighbors. There's a famous example of this called the game of life. In the 1970s it was a popular game to play because people for the first time were working with what was then called the personal computer, which is nothing compared to what is now. Now it's just a simple laptop. It was still a big machine. But you could work on it and you could play the game of life. It was a universe defined on a lattice and had an evolution law, and you can switch it on the computer and see what happens with certain initial conditions. Now, if the evolution law has a very simple form, special form, called the Margolis rule, then you can easily say that it can go forward as easily as backward. That is important for certain reasons. For instance, on the spot labeled A on that graph, so that's here, this A here, at this A, I can define the position, the contents of this cell here, which come to a number of bits and bytes, to be equal to the contents of this cell here in its direct past, but then you add to it a function of its nearest neighbors B. And for cells of the type B, you do the same thing. B1 goes into B2 plus a function of these A's. If you phrase your evolution law this way, you can go forward in time as easily as backward in time. And that's a nice subset of all cellular automata. The game of life did not belong to that, but that's a detail that, okay, I won't have time to discuss here. But here I have the time reversible cellular automaton. Its evolution law is just, again, a permutator, and you can invert it. So its evolution law, when you write a representation of it, it must be a unitary operator. Therefore, its eigenvalues, again, like on the unit circle. Operators of the type A form a unit circle e to the minus IA, and it so happens that on one line, all the A-type operators commute. So you can also say that the evolution operator is a sum of objects which describe the evolution of just one cell. And so you can define all cells of the type A to form together a unitary operator e to the minus IA, where A is just a sum of A's at a point X. Same thing for the operator of the type B, where B is a sum of local terms B of X. But the entire evolution operator intermittently does the A-type cells and the B-type cells. And the A and the B do not commute. So the A's all commute, the B's do not commute, but they only are non-commuting when X and X prime are neighbors. Then they don't commute. Now, how to find the Hamiltonian? Well, you want to write this thing as e to the minus IH, that's a product of two other exponents. There's a nice expression for such a product. It's called the Campbell-Baker-Hausdorff formula. It tells you that the product of these things can again be written as exponents A plus B plus commutators plus higher commutators, and on goes the series. If you were allowed to terminate the series, then here you would get a local-looking Hamiltonian. Not quite local, it contains neighbors terms, and next to neighbors terms, and so on. But if you terminate the series, it is a more or less local Hamiltonian. Hamiltonian which is a sum of Hamiltonian densities, just like in the real standard model. So this starts to look quite a lot like a standard model. And for a time I was totally, enthusiastic about this model because it looks so much like a quantum field theory. However, the Campbell-Baker-Hausdorff series does not converge. And that non-convergence is going to be very important later for having more nasty discussions about this theory, which at first sight looks like generating a quantum theory. This is a genuine Hamiltonian in the quantum sense. I can do this in the representations of Hilbert space. So that was the most complicated example, which I mentioned, which is mathematically wanting. So I can't solve the cellular automaton, certainly not if it is a generic or universal automaton. It has been shown by computer scientists that this Margolis rule is enough to generate a computational universal cellular automaton, which means that you can do any computation with it, and you can mimic any other model with it, so it's going to be very complicated. The cellular automaton interpretation of quantum mechanics is now the following. I just assume the existence of Beables. I can't prove that. Certainly for the standard model, I haven't found anything looking like Beables. But in the converse, I can find many, many quantum theories that look like the standard model in some very distant sense, and where I start from the Beable theory. So the statement that there exists no Beables for the standard model is certainly very difficult to prove, and I think it's not possible to prove. It's always possible to assume the existence of Beables. So my interpretation rests upon an assumption that these Beables exist. And I claim this assumption is far from crazy. If you make this assumption, then a lot of so-called quantum mysteries drop out of the air right away, and everything becomes very simple if this were true. So my interpretation is I assume this to be true, and let's see to what this leads. And for instance, if you can do this more or less locally, and you can generate a local Hamiltonian, then it becomes a local hidden variable theory. Why hidden variables? Well, the contents of these cells are classical, so they could be called hidden variables. Why hidden? Well, that's a more difficult story. Suppose I have done such a thing, and I've succeeded in finding Beables, and I have an ontological basis, the Beable basis. So the basis in terms of which all the Beables commute, all the operators commute, is called the ontological basis. Now, any other quantum state, which sits in a different basis, can be found by superimposing quantum mechanically all these Beable Beable states. There's nothing against that. I claim a superposition, just like what Breuer Kaufmann did when she wrote down a solution of the Ising model. Those superpositions are just man-made, but very useful. So I call those templates. And then anybody comes with a hydrogen atom or other complicated quantum system, the standard model, I say all these states in which you defined the hydrogen atom or the standard model are template states, as opposed to ontological states. So all you have to do is make unitary transformations. And you know about the theory of quantum mechanics. You are free to make any unitary transformation you like. We do that all the time. When you Fourier transform a quantum particle to go to momentum space, that's a unitary transformation. But it's like a rotation in vector space. If you go from the position states to the energy eigenstates, there's another unitary transformation. You can make as many unitary transformations as you like. I now claim there may well exist a unitary transformation that brings me to an ontological basis and ontological operators. If so, that would explain a lot about the mysteries of quantum mechanics. All the template states would be quantum superpositions of ontological states. Conversely, all the ontological states would be quantum superpositions of the template states, which I usually use when I do a quantum calculation. So this is basically the opposite of that. And yeah, something strange. Okay, well, anyway. Now, when I do this, I will declare lambda absolute square to be the probability. So suppose that I'm using a template instead of an ontological state to do a quantum calculation. Mind you, the template states, just like the ontological states, all obey the same Schrödinger equation. So if I take a superposition of template states or a superposition of ontological states, they obey all the same Schrödinger equation. Therefore, the coefficients alpha and those coefficients lambda are time independent. That's very important, that the coefficients of the superposition are time translation invariant. If I chose my lambdas once, they'll be the same at all times. So if I take lambda squared to be the probability that I have an ontological state, then that allows me to normalize the template state to 1. Then the sum of the probabilities is equal to 1. And these probabilities will be conserved. If I have one ontological state, it evolves like this. Other ontological state evolves like that. If I have a probabilistic distribution of ontological states, the probability distribution will just be described by those very same lambdas. The point, the fact that I took lambda n squared and not something else, actually you would be free to take something else there. It would still be true. But nobody does that for very good reasons. Because if you apply unitary transformations, only lambda squared is invariant. So if you would put anything else in lambda squared, you would have hell of a problem in making any unitary transformation. So if I say all unitary transformations are legitimate, other transformations are not, then I'm forced to use the square here. This looks like a hidden variable theory. No, these are pure states. I am not introducing mixed. You could introduce mixed state if you want, but I'm not doing that for the time being. I don't see any. Well, one could think about the role of mixed states later, but for the time being, I limit myself to pure states. So for instance, when you analyze an LHC experiment, you have your initial state and your final state. All these it suffices to consider them as pure superpositions of these templates or pure superpositions of ontological states. I'll come to that. I'll come to that. So please remember your question. If it's not answered in a few slides, then ask it again. Now I want to talk about classical states. A classical state is a macroscopic state, like us sitting in this room, like a planet moving around the sun, or like the dial of a classical machine, like a scale when I weigh myself or when I measure something. All these things are classical states. And now comes a statement that got people confused. And that is a statement that classical states are ontological as well. And the argument for that goes as follows. Imagine a planet. A planet is very, very large. So now take one very tiny grain of the planet and take a cubic millimeter of a huge planet like the Earth. Take a cubic millimeter. Now suppose that in the cubic millimeter I can say that there are thousands, billions of atoms in that cubic millimeter. Having all these atoms may allow me to distinguish that state, that ontological or non-ontological state, to distinguish it from the vacuum state. There is a vacuum state, which is a superposition of ontological states. There is a state of the planet, of 1 cubic millimeter of the planet. Suppose that it deviates microscopically from the vacuum state. And suppose that I can recognize from the ontological states whether this is a cubic millimeter of rock or a cubic millimeter of vacuum. And suppose that there is a way to distinguish that with only a very, very tiny probability that is nearly indistinguishable, but not quite. If that holds for a cubic millimeter, now take the entire planet. If I could distinguish the cubic millimeter only a very little bit from the vacuum state, then certainly I can distinguish the entire planet from the vacuum state. So the planet will be completely orthogonal to the vacuum state. So not all ontological states will be vacuum. Some will describe planets. And so for the planet, it becomes nearly inevitable to say that a planet can be identified by looking at the ontological states. The ontological states are assumed to sit at the Planck scale, so they're very, very tiny and complicated. But by doing statistical analysis of the states at the Planck scale, I might be able to figure out whether there's a planet here or whether I have a vacuum, because the planet is so big and massive. If this holds for a planet, it will hold for anything classical. So that includes the blinking light of an indicator of a measuring machine, or the trail in a bubble chamber of a particle, and so on and so forth. Everything that can be identified classical will be ontological. So I'll be able to use Beables to describe a classical state. Now remember that actually you could call this an axiom, because I cannot really prove it. I can make it very, very plausible. And I think my argument is plausible to make this an ingredient. I found it to be an essential ingredient. Let's use it as an axiom in our model, although I think I can argue that it would be very difficult to imagine otherwise. So assume that classical states are ontological. And now paraphrase a simple experiment. So remember that the templates are superpositions of ontological states, where these lambdas are time independent. Now think of doing a quantum experiment. What do? You have particles in a plane wave, but the plane wave is not ontological. So it will be a template state. It will be a probabilistic superposition of billions and billions of ontological states. All these are described by this coefficient lambda. Lambda n tell you the probability that you have one particular ontological state. The plane wave is not ontological. But the probabilities are lambda squared. Now compute the final state. The final state will again be a template, but now the template can be compared to classical states. So a particle moving in a plane wave in that direction can be said, well, the detector will go off in that direction. That detector is classical. So now the final states are basically classical states, but they have the same lambdas here. So what you have to compute now is take the classical template. The classical template will be lambdas times classical ontological states. But now remember that the lambdas were time independent. So the lambdas you started off with at the very beginning of the experiment are the same as the lambdas you end up with when you do your experiment, when you interpret your experiment, you do your measurement. So that leads to the Born rule. I said lambda n squared were the probabilities in the beginning when I introduced a template state to describe the initial state. Now the same lambdas turn up as the probabilities for the final classical states. So these lambda n's are now the Born probabilities. And this is actually almost a derivation of the Born rule. It's like what I think was called the Gleaver theorem, that the Born rule is practically the only rule in quantum mechanics that you can use to describe probabilities. All others will lead to inconsistencies. Here I say, well, actually I assumed it by saying that a template state is some lambda times ontological states. Those lambda squares must be probabilities, because what else can they be? But that, once you say that, they will turn out to be the Born probabilities. That is to say, the absolute squares of the coefficients will be the probabilities that you find a system to end up in a given classical state. Of course, the measurement leads to classical states. So this is how I now interpret the classical problem. And the Born probabilities just tell you what it is. So remember, ontological states are formed on an orthonormal set. And superpositions of ontological states are never ontological states themselves. So you never end up in a superposition of classical states. You always end up in classical states themselves. And this leads to two important observations. One is the problem of the collapse of the wave function. So basically, the final state will be a classical state and never a superposition of two different classical states. So there always has been the question, how can it be that the wave function collapses into a delta peak, describing one single classical particle, never a superposition of two different classical states? The reason is the classical states were declared to be ontological, and single ontological states always evolve to single ontological states. All I have to assume is that the universe started off at the Big Bang. The universe started off in the ontological states. Ever after that, the universe stayed in the ontological states. I'm using template states all the time to describe quantum mechanical calculations, but they end up in ontological states just because the universe started off in ontological states. I didn't know that, but now here you see an example. That's why a wave function always collapses into single classical states, because this ontological property of the universe is conserved in time. Same thing for the famous Schrödinger cat. There always has been a problem that you probably all know the Schrödinger cat story. That you have an experiment where, depending on the quantum outcome of an experiment, or you do a measurement, if the measurement gives a 1, a box with a deadly poison opens up and the cat dies. If the measurement gives 0, the cat stays alive. If the original system was in a quantum superposition, what will the cat be? Will the cat be in a quantum superposition? Answer no. The wave function collapses. The cat will be either dead or alive according to probabilities. And now you see, in this theory, it has to be like that. The superposition of a dead cat and a live cat is not a classical state and is not a ontological state. If you assume the universe to start off in an ontological state, the universe can end up only in either a dead cat or a live cat with the quantum probabilities in place exactly where they should be. So this actually also removes essentially the Schrödinger cat problem. How do quantum operators arise in a cellular automaton at all? A cellular automaton is classical. Now, I want to show to you very briefly a fundamental classical system called the planetary system. Imagine, right, here we are. Imagine the solar system as the prototype of something classical. How do I introduce a quantum operator in such a thing? I claim even the solar system. Forget about the fact that actually inside these planets there's quantum mechanics. But think of the thing described by Newton's equations, which are totally classical. I can introduce a quantum observable in the system nevertheless. And that's the Earth-Mars exchange operator. The Earth-Mars exchange operator puts Earth where Mars is and Mars where Earth is. Now you might complain, how do I measure such an operator? Do I have to take planet Earth and put it where Mars is and take Mars where planet Earth is? How do I do that? I can't. No, sure you can't. Nobody can. But have you ever tried to interchange two electrons? I don't think you can do that either. So, whereas in the case of quantum mechanics of electrons, it's very common to consider the operator of exchanging two electrons, even if you can't exchange them. You can't exchange Earth and Mars, but you can consider what happens. This operator, by the way, oh, yes, you have to leave the velocities as they were on their spots, but the fact that this non-trivial operator comes from the fact that the mass of Earth is not the same as the mass of Mars, and therefore the evolution of the system will change quite drastically if you make such a displacement. For instance, you can ask what happens with the moon, and what happens with the moons of Mars. Well, I didn't even touch that question, but that's obviously a very complicated operator. One thing we know about the operator, if I square it, it's 1. Because if I apply the operator twice, I get Earth back where Mars was, where Earth was, and Mars back where Mars was, and that's the identity operator. So the square of the Earth-Mars operator I know is 1. So the operator is plus or minus 1. So now someone may ask, let's measure that operator. Ah, you can't. It would be a counterfactual measurement. You can't measure that operator. It's plus 1 or minus 1. It's actually a quantum superposition of these two states. Because we know that Earth is here and not there. We know that Mars is there and not here. So we have the sigma x eigenvalues of that operator. We don't, or you could say sigma z eigenvalues, depending on how you define sigma z and sigma x. But we don't have the eigenvalues of this interchange operator. It's of course just like the Pauli matrices. We can't actually measure that operator. But you can define it, and according to Copenhagen, this would have been an observable, even though nobody can actually measure that observable. That's because we happen to be in the wrong eigenstate, that's all. So there's nothing special about this system as opposed to quantum systems. And so I return to this. There we are. So it's an operator which is plus or minus 1, and measuring it is counterfactual reality. Then I only have a few minutes left. And of course, the basic question everybody now asks, what about Bell's theorem? Because Bell has practically disproven the existence of hidden variables. And I have no time to exactly explain what Bell's theorem is about, but it's all about having an observer here called Alice, having an observer there called Bob, and Bob and Alice have detectors by which they detect two entangled particles. Entangled particle emitted by an atom which sits at the system S. Time runs here vertically, horizontally in space. Thin lines are quantum systems, thick lines are basically classical systems. These Qs could be very distant quasars upon which Bob and Alice react when they decide what to measure and what not to measure with these entangled particles. Enfin, Bell derives a straight contradiction when you think of this setup very precisely. The contradiction that Bell arrived at could be removed if you assume 3 body correlations. That is to say, the setting that Bob chooses and the setting that Alice chooses could be correlated to the setting that the 2 entangled photons choose when they leave this atom. Then that's too simple, because then people say, yes, but Bob and Alice have free will. What about that? My answer, in a cellular automaton, you have no free will, because a cellular automaton determines classically what happens. It will also determine what Alice and Bob will be doing. So they have no free will. Well, that's called superdeterminism, but that's not good either. Sorry. My daughter is calling me, but she's calling me at the wrong moment. So people say, no, this is absurd. And they come forward with a little story. Actually, I have not so much time left. Let me tell you a mouse dropping story anyway. They said, suppose Alice and Bob carry both with them a cage with a mouse in it. And at T is T1, long before the measurement is done, but just after the photons have been emitted, both Bob and Alice count how many mouse droppings the mouse did. If the number is even, Bob chooses this setting. If the number is odd, Bob chooses that setting. Alice also, if her mouse has an even number of droppings, she chooses this setting. If there's an odd number of droppings, she chooses that setting. And now what I'm assuming is that the number of mouse droppings is causally connected by a correlation law to how those photons came out of the atom. And then what I hear from people all over the net say, this is absurd. How could that atom know how many droppings the mouse will make? The mouse may not yet have been born when the atom was decaying. Yes, the photons already knew how many mouse droppings would come out. Isn't this totally absurd? I calculated the correlations you need, and it goes like the absolute value of a sine function in the most favorable example. Sometimes you need even stronger correlations, but this roughly is the correlation function I need. So this is what people call absurd. And but you have to remember my statement about the ontological states. All these, we are all using template states. The atom decaying into atoms was a template state. Bob and Alice were using template states to set up their polarizers and so on. But you have to see how these template states are composed as quantum superpositions of ontological states. How is a decaying atom distributed in terms of ontological states? Well, that also are template states, so you have to complicate the amount of work to describe them as ontological states. But now comes a very important observations, and actually I won't go through this argument too much, no. The ontological states obey a conservation law. The universe started off at the Big Bang in an ontological state. That's a very important, non-trivial piece of information that you have to use. Once it is in an ontological state, it will always be in an ontological state. So this decaying atom will be in an ontological state. These mice with their droppings will also be in an ontological state. In fact, these mice are classical, so they certainly will be. So eventually, Bob and Alice will only measure ontological things. The ontological conservation law allows us to have correlations. There could be also the correlations between the ontological states, including the correlations of this mouse dropping function. So I claim this is not in contradiction with anything we know about physics, even though it looks pretty absurd from the point of view of this mouse. Yes. So it might mean that actually I'm skipping some things. You may read them when you look at the slides when I put it on the net. I'll just now say some things about conspiracy, that the ontological states will be have exactly the same coefficients now as they had in the distant past. That is a conservation law. If the state started off ontological in the far past, according to this very special standard model which allows for an ontological basis, these ontological states will continue to evolve in terms of into an ontological state. That is going to be the resolution of this problem, but it's not easy, and I need a lot of convincing. There is, however, an anticlimax, and I'm running over time, unfortunately, but I'll briefly mention the anticlimax. And that is, there is a difficulty in finding a version of the standard model that admits for an ontological basis. And that is, again, the positivity of the Hamiltonian. I mentioned the second quantized theory of the neutrino, saying that that has a ground state. So that is all we need. Right? To do quantum mechanics, you need a ground state. I have a ground state, yes, but that's only when these neutrinos are not really interacting. When I have an interacting theory and try to apply second quantization, I run again into the difficulty to show that the interaction Hamiltonian still allows me to have a ground state. And that turns out to be very difficult. In many models that I tried to get something that looks like the standard model, I either get Hamiltonians which are beautifully commuting when they are far away. So if x and x prime are bigger than some epsilon away from each other, then this commutes. And I want Hamiltonians bound from below. These two contradictions seem to be at least somewhat at odds with each other. It's very hard to obey both. And this is what a smarter critic of my work would point at. that this difficulty you have not resolved. No, I have not resolved it. But I think that the answer is gravity. In gravity, everything changes. In gravity, the Hamiltonian plays another important role. First of all, the Hamiltonian is the integral of Hamiltonian density. That's now in gravity, that's density of energy distribution. And in gravity, that generates a gravitational field that causes curvature of space-time. And that is classical. So according to gravity, the energy momentum tensor should be classical. That's very strange because the Hamiltonian in a quantum theory is not classical at all. It's the evolution operator. Does not commute with the Beables. So there's a very difficult situation with gravity. And I think gravity poses me so many problems that I think all problems have to be solved together in one go. So my suspicion is that gravity might give an answer. Remember that the problem of the positivity of the Hamiltonian is an extremely technical one. I tried all sorts of technical solutions. I always nearly got there, but not quite. And that's because I haven't dared yet to introduce the gravitational force here. And I suspect one has to. And that, in turn, may be related to the hierarchy problem. The fact that gravity acts at a totally different time and distance scale than the other forces of the standard model. So we still have 20 or more orders of magnitude to go from the standard model and LHC to where gravity plays a role with black holes and everything. That's 20 orders of magnitude. Over 20 orders of magnitude, lots of things can happen. So the Hamiltonian may acquire a ground state while traveling over these 20 orders of magnitude from the Planck scale to the standard model scale. I don't know this. This is a very, very difficult question. I could add to this that positivity of energy is a problem with the gravitational field. The gravitational field, I don't know whether you know this, the gravitational field carries a negative energy density. A large amount of negative energy density sits in the gravitational field. So positivity of energy gets a serious blow anyway when you switch on gravity. So that you have to take into account, together with the notion of positivity, of locality. These are very serious and extremely difficult technical questions. And those I cannot answer. So because of that, you have to take my interpretation theory on faith. I cannot prove it because I cannot make models that look like the standard model as much as I want them to look like the standard model. So this is the end. Thank you.
Thank you very much. So is there a question?
I'd like to know your comment about the weak measurement proposed by Aharonov. So Aharonov proposed such a measurement to consider a Schrödinger state without breaking the wave function itself. So in your interpretation, how can you interpret it, the weak measurement itself?
I claim that these theories I'm describing are quantum mechanical theories. So anything you say about measurements, whether it's weak measurements or other measurements, can be mimicked in these models. So if Aharonov comes with such an idea, I have no objection at all to this way of trying to measure things. It doesn't mean very much to me because I think, well, I mentioned the entangled photons. It's part of the system. Quantum mechanics, of course, needs entanglement. And that's, of course, a central ingredient of also these weak measurement proposals, is the idea that particles can be entangled. It's very important to allow that, and that is, of course, the notion of locality driven in a made rather difficult. And my inability to reproduce a standard model also makes it difficult to me to show exactly how entangled particles can nevertheless lead to classical measurement results, let alone when you make weak measurements. So all that will still have to be done.
There are any other questions?
in the first part of your talk, you introduced a fundamental time scale, delta t. So I'd like to know the typical scale of the delta t in your story.
Very good. No, that's an important question. As you saw in the harmonic oscillator, I could choose delta t arbitrarily small by taking more and more energy states. Eventually, I could go all the way to the Planck scale and say, well, the inverse of that will be my delta t. But eventually, I believe delta t to be finite, just because I have a limited number of states. Think of physics at the Planck scale, and I cut out a very tiny region of the universe, then I have only a finite number of discretized quantum states left. So if they evolve classically in any sort of way, then my time should also be allowed to hop from one to the next. My belief is that in the most reasonable theories of determinism, my delta t will probably be in the order of a Planck scale, the Planck time. That's the most likely. I would choose it to be there if I had any choice. There is, however, one thing. There is, however, a version of string theory where I apply this. I can write down the Beables for a string theory. There, delta t is the Planck scale multiplied by the square root of alpha prime. So, and alpha prime could be small in Planck units, and then the time scale becomes large in time units in Planck units. So the time scale could be quite a bit bigger than the Planck scale.
There are other questions? So if not, let's thank again.